Bien, c'est un grand plaisir d'accueillir Jacqueline Bloch aujourd'hui. Je crois que beaucoup d'entre vous connaissent Jacqueline, donc je ne vais pas la présenter pendant longtemps, mais je voudrais juste dire quelques mots. Je la connais moi-même depuis bien longtemps maintenant. Jacqueline a fait sa thèse, a soutenu sa thèse en 1994. Elle a fêté un anniversaire rond il n'y a pas longtemps, à l'Université Paris 6. Et elle a été recrutée immédiatement au CNRS. Bravo. Pour aller travailler à Bagneux, c'était encore le CNET?
Non, alors nous, on était dans un laboratoire du CNRS qui s'appelait Laboratoire de microstructure et de microélectronique. L2M, c'était dans les locaux
C'était dans les locaux du CNET.
Mais on était une unité propre.
Mais le CNET
CNRS
existait encore à cette époque-là.
Bah oui.
Oui. Non, mais je crois que c'était 2 ans ou 3 ans avant que le CNET a dû disparaître en 1996, je crois. Enfin, disparaître. Les labos ont été repris à Bagneux. Donc, elle était là, recrutée au CNRS, de toute façon, pour travailler à côté du CNET à Bagneux. Elle a fait un stage qui n'est pas un stage postdoctoral, puisqu'elle était déjà au CNRS.
C'est postdoctoral, mais c'est post-permanent.
Post-permanent. Oui. Au Bell Labs, ensuite, dans les fin des années 90, dans lequel elle a travaillé sur des choses qui ensuite l'ont rendu célèbre. C'est toute la génération de petites boîtes quantiques. Et génération de lumière avec ça. Donc, un de ses grands faits d'armes, c'est d'avoir réussi à obtenir le couplage fort de ces microcavités, donc de ces boîtes quantiques avec des microcavités réalisées elles-mêmes avec des miroirs semi-conducteurs. Ça, c'est le début des années 2000, je pense, le couplage fort. Voilà. Et ça, je dirais, ça a donné naissance à plein de choses, toute cette physique des polaritons de cavité. Jacqueline est célèbre, entre autres choses, pour avoir bien précisé qu'un condensat de polaritons, ce n'était pas la même chose qu'un laser. Voilà. Et donc, je dirais, les condensats de polaritons te doivent beaucoup, parce qu'on en était encore à débattre si c'était des lasers ou pas. La vie serait différente. Et puis, depuis, elle a fait plein de manips superbes. J'ai abondamment pioché dans leurs expériences dans les cours précédents sur la topologie, où ils font des chaînes 1D pour faire des chaînes SSH, du graphène artificiel, enfin plein de belles choses. Donc, je vais lui laisser sa parole, je ne vais pas parler plus longtemps. Je voudrais juste te dire qu'elle a eu plein de grands prix, le prix Jean Ricard de la Société française de physique, le prix Ampère de l'Académie des sciences. Elle est membre de l'Académie des sciences depuis quelques années. Donc, c'est vraiment un très grand plaisir de t'avoir avec nous. Merci.
Merci beaucoup. Alors, tout d'abord, je voudrais remercier vraiment très chaleureusement Jean pour m'inviter ici. C'est toujours impressionnant de passer après Jean Dalibard, qui fait des cours absolument extraordinaires. Donc, quand on l'écoute, on se dit « Oh là là, mais moi, ce que je vais raconter, c'est pas clair, c'est pas ça. » Bon, ce sera ce que ce sera, c'est pas grave, vous me pardonnerez. Alors, la première chose que je voudrais savoir, c'est if there are people who cannot understand French in the room. Don't be shy. Okay, so I will switch to English, and so you will have the great pleasure to listen to my beautiful English. And so what I wanted to discuss today, so since Jean is talking about solitons, I wanted to talk a bit about solitons, and at the same time, I wanted to talk about recent topics that we explore these days. And so what I've decided to talk to you about is about topological photonics with our system, which is our Excitonic Polaritons. So it's going to be strongly related to the previous lecture, a series of lectures from Jean Dalibard at the Collège de France in 2018. And I chose these topics because one of the key advantages of polaritonic system is that we have a strong nonlinearity. We can implement some topological properties, some Hamiltonians with some interesting topological physics. And at the same time, we have this kern nonlinearity. So one of our research axes now is really to see what we can do. Is there new physics that we can discover about topology, looking at a system with strong kern nonlinearity? And so we will see some solitons, which are called gap solitons, because we will create these solitons which are bright in a gap of a band structure. And so we will, in particular, address the question whether the presence of a gap soliton in a chain can induce topological properties, can modify the topology of a system. So let me first present the group. So we are working at the Center for Nanoscience and Nanotechnology, which is at the heart of the Paris Saclay campus. And so the logo of the C2N is this one, and it's actually a top view from the building where we are, and the green square is the clean room. So we have actually a very big clean room, and then many experiments going on. And so we are doing optics on micro and nanostructures, which are fabricated in the clean room of the lab. So we, who are we? So the group, we are two PIs, Sylvain Ravet and myself. So Sylvain is in the room. He's a young researcher from CNRS. And we have also a very strong collaboration with Alberto Amo, who was before in the group and is now having his own group in FLAM laboratory. And so here you have a picture of many people who work with us, so young PhD students and postdocs, and also permanent people working in the C2N, so researcher and engineer, and these are permanent people who are working in the clean room, very close to technology, develop a strong know-how that we share in the lab, and that is improving from days to days, but over a very long period of time. Then I want to mention also that we have a lot of collaborators, so theory collaborators. And for example, I'm going to talk a lot about work we have done in collaboration with Nathan Goldman and also with Jacopo Carussotto, so all these people. So in red are the people who have been really involved, the young people involved in the work that I will detail today. Okay, so topology. So first, so probably most of you are already very familiar with that. So in 2016, there was actually a Nobel Prize to these brilliant people, Taules, Alden, and Kosterlitz, who are the people who really understood that topology, so which is a branch of mathematics, can be a very efficient tool to describe some physical phenomena and give some very strong insight into the physics, a different perspective. So for instance, the quantum Hall effect, it's very interesting to revisit the quantum Hall effect using these concepts. And when I was in Master 2, I learned a lot. We were working a lot, calculated in detail the quantum Hall, and there was nothing about that. We were just addressing the Hamiltonian, the Bond structure, the motion of electrons in a magnetic field, and never talk about that. When we could explain everything, there was no need for that. But actually, it has been very useful, as we will see, to talk about this kind of mathematical properties. So the idea is that before that, we were essentially talking about energy of quantum particles, wave function, and describing the dynamics of system using, for example, the Schrödinger equation. Topology is something more subtle, which in addition to this kind of quantities, consider some quantities which are somehow encoded in the wave function and which are global quantities, so you calculate them locally for different values of k, for example, but you integrate them over the whole phase space, over the whole Brillouin zone, and you get actually integers, so numbers of quantities which are integers and which are characteristic to the system, to the band, for example, that you consider, and which can be very robust to local deformation. And so, for example, if you look at the quantum Hall, the quantum Hall effect, so the motion in 2D of charged particle under a magnetic field, you can relate actually the quantification of the conductance to integer, and you can actually see that these integers are so explain to you why the resistance, for example, here is just related to an integer and some very, very fundamental constant, like the Planck constant or the electron charge. So this is just a general introduction, and so the consequences of considering these invariants, you have very remarkable consequences. For example, the first one is that if you take two materials with different topological invariants, you cannot actually go from one material to the next without closing a gap and reopening a gap. So you need to close a gap, and the way you can close a gap is by having an edge state. And so you can actually deduce from topology the existence of edge states at the interface of two materials with different topological invariants. Another effect, which is very striking, is the idea that you can actually induce transport for particles in a periodic potential without applying a force, but just modulating in time the potential in which these particles live, modulating slowly, so in an adiabatic way, so which does not allow particles to go from one band to the next. They stay in the same band. You go back to you modulate the potential in a periodic way, and so when you come back to the initial condition, the potential is the same, but the particle has moved by an integer number of the unit cell of your periodic potential. And you can also relate this motion, the number of times you have moved, the number of unit cells you have moved, to some topological invariant. I will come back to that later. So these are two physical consequences of the existence of this kind of topological invariants. So one important step was then, so before everybody was looking at, for example, the quantum Hall effect and considering that this was really the physics of fermions. And indeed, to get the quantization of your resistance, you need bands to be filled. So you need fermions and you fill the bands. And then there was this very important paper by Alden and Raghu. So this is a peer A, but there is also a peer L at the same time where they give complementary information. And I like very much this paper because it really tells you that indeed the quantum Hall effect involves the filling of bands according to the Pauli principle. And so it's essentially a fermionic effect in nature, but the existence of the edge state is a property of the one electron band structure, and it doesn't require any Pauli principle. And this suggests that this physics is not restricted to fermions. And actually, this leads to the idea that you could get topologically non-trivial topological edge states looking at two materials with two different Chaire numbers, and this could work with bosons and with neutral particles. And so this is somehow the beginning of topological photonics, where we are going to use photons. And in parallel, then, there was also the idea that you could use also neutral atoms, and I want to refer to this beautiful review of modern physics, which explained really how you can implement artificial gauge fields for neutral atoms and look at this kind of topological physics with atoms. So here I'm going to concentrate on topological photonics. And so why do we want to do the topological photonics? So first we can indeed implement, for example, the integer quantum Hall effect. So here you see this was done in the microwave domain in 2009, and then more in the infrared with rings of silicon ring resonator. So this is a beautiful work from Mohammad Hafizi. But so then you can just reproduce the physics of electrons, but then it can be interesting to ask you the question, what can we do something beyond that? Can we use ingredients that are related to photonics and play with topology in this context? So what do we have in photonics? We have gain, and so here, for example, you can see a topological laser. So you have two photonic crystals with different topological invariants, and you manage here to actually laser on the edge state, which is present at the frontier of these two materials. And depending, so here you have to break time reversal symmetry. There is a little magnetic field. So depending on the direction of the magnetic field, the lasing mode rotates in one direction or in the other. And then there is a waveguide coupled to this edge state. So you see the light coming out either through this in this direction on the right or on the left, depending on the direction of the magnetic field. And then you can play with nonlinearity, you can play with gain and loss, PT symmetry, and then you can also, in a photonic system, resonantly drive the system. So send a laser and inject photons in the mode that you want. And if you have nonlinearity, you can actually stabilize nonlinear steady states, which are not stable if you just let shine the laser or if you have a closed system, but that you can force and drive coherently if you have a driven dissipative system. So this is exactly what we do. We have an array of coupled resonators, so we can couple different sites. We have some interaction, so some Kerr nonlinearity. It's a weak interaction for the moment, so U over gamma is small enough that in all the experiments I'm going to describe, we are in the midfield. This is a semi-classical regime. But if actually interaction becomes stronger, if you start to include fluctuations, then correlation, then this is really an experimental implementation of a driven dissipative Bose-Hubbard model. And so then what we are going to do is to engineer, so there is loss, so if you want to reach a steady state, you need to pump the system, and you can pump each site of the system with a given energy, a given phase, and start to play, to monitor the properties of the system. So the outline of the talk will be the following. First, I'm going to introduce a bit more the system, so what these cavity polaritons are. And then I will address a few recent work that we have realized. And first, we will stay in 1D. So I'm going to look at 1D chains, and we will look at the SSH model, as Jean Dalibard mentioned. And so then we are going to play with nonlinearity. So we are going to pump resonantly and reach different steady states and look at what is going on. Then I will describe also a proposal that we developed together with Sylvain to implement actually in a 1D lattice a tau-less pump, a topological pump. So that's going to be the first part the main part of the talk. And then I will go to 2D lattices, and I will explain an experiment that we implemented recently. So this is really a work driven by Sylvain. To access experimentally topological invariant. So to really measure the Bloch eigenmodes. And so as you saw, the Chaire number is related to the derivative of these Bloch modes over the whole Brillouin zone. So we are now able to measure the Bloch states over the whole Brillouin zone. This we will demonstrate here in a two-band model, but we can do it in multi-band system. And so this will allow to access experimentally Berry curvature and Chaire numbers, which is a super important tool. So that's my plan, the menu of the day, and I hope we will have time to reach the dessert. Okay? So the introduction is the system. So we are playing, essentially we have a Fabry-Perot cavity. We have two mirrors, photons confined within the cavity. So we use the system which is the most controlled, which is an old friend. So it's a semiconductor which is very well known for optoelectronics, so gallium arsenide, aluminum gallium arsenide. We can grow very high reflectivity interferential mirror. So we do the whole structure is grown atomic layer by atomic layer to fully control and get the best structure as possible. So the cavity mode has some dispersion. If you consider different angle of incidence, the resonance occurs for different wavelengths or different energy. And so here we plot the photon dispersion, the cavity mode dispersion, as a function of the angle of incidence, which is equivalent to the in-plane wave vector of light. Then to get this nonlinearity and not have a passive system but an active material, we insert at the antinode of the electromagnetic field one or several quantum wells. So these are regions of lower band gap in which electrons can be trapped. And so these quantum wells, they can absorb light, and then they can re-emit light. This is an active material. And so if we we create electron-hole pair in this system, they can bind by Coulombic interaction and form an excitation, which is called an exciton. It's an electron-hole pair, like an hydrogen atom, which is bound, has a state, which is called the 1s exciton state. And this exciton can move in the plane of the quantum well for a certain time, and then they can eventually recombine. This is an excited state of the semiconductor and go back to the ground state. So we can plot also the dispersion of exciton as a function of their in-plane wave vector. So there is a motion of the center of mass. And if we plot them on the same scale, the exciton looks completely flat because the mass of the exciton is like 4 orders of magnitude larger than that of the photon. Okay, and then we designed the structure so that photons are quasi-resonant. The cavity mode is really close in energy to the exciton, so that when an exciton emits a photon, the photon oscillates within the cavity, can be reabsorbed, re-emitted again. At the end of the day, we get the strong coupling regime, and so we have no more exciton or photon, but really mixed exciton-photon states, which form these two bands, the lower and upper polariton bands. So we are interested in this polariton, and I've been working, as Jean reminded, on this system for so many years. And why is it? Because really the fact that we have a mixed particle gives this system super interesting properties. So essentially in the present talk, I will use the property of photon, of the photonic component, which is that it has a very light effective mass. And because of that, you can confine the system in micron scale structure. You see that if I take a finite system of 1 micron, I'm going to discretize the states essentially with an energy scale which is 1 over A. So if you take 1 micron, you get a confinement energy which is of this order. So this is already very much larger than the line width. So you don't need to go to nanoscale. Micron scale for lattices is enough, and so it's much easier to implement and to control, in particular in terms of disorder. We are going also to use the polarization. So photons have a polarization, so polaritons have a polarization, and so this can be used as a pseudospin. So we are going to engineer not only the wave function, but also consider the pseudospin. And actually, you can also get spin-orbit coupling, so playing with the polarization property of the cavity, which is also very important for topology. And then, concerning exciton, so the excitonic component, we will have a strong Kerr nonlinearity, which is going to be the key to get solitons, for instance. And also, you can break time reversal symmetry by using the Zeeman splitting that exciton acquire under a magnetic field. So these polaritons, they have a very strong response to magnetic field, and you can induce a Zeeman splitting, which is also very important for topology. Okay, so how do we probe these polaritons? So we excite the system, we can populate the bands, and then we can look at the emission that comes out from the top, at photon escaping the cavity from the top. And if, for instance, you look at the photon escaping the cavity as a function of angle and energy, which is energy and wave vector, you can directly probe this band dispersion. So this is an image which was taken on a single click of a CCD camera. You project the Fourier plane of the collection lens of your setup, and you get this image. And then you can probe the different states, looking at their intensity. You can also look in real space. You can look at where the light comes from. So this is, for example, a honeycomb lattice, which is lasing, and you see the emission from each pillar. It looks like a PowerPoint, actually, drawing, but it's not. These are raw data, what you see when you look at the lasing emission. And then, also important for this talk, we can do interferometry. We can use the phase, we can measure the phase of the light that comes out. Okay, so then to engineer lattices and control the band structure, The easiest way, the one that I'm going to describe, is to really use a tight binding approach. So you take orbitals that you organize on a lattice, and then you couple them. So this is what you use when you look at the band structure of crystals. You take orbitals of one atom with different orbitals, and then you couple them and you form the band structure. So our elementary building block, so our photonic atom, is going to be a micropillar like this. So you have to imagine that the cavity, the layers, the mirrors, and so on are vertical. And we have etched using electron beam lithography and etching. We have etched all the material that was not protected by a mask that was deposited on top. So you have this kind of structure where light is confined vertically between the two mirrors and laterally because of the index of refraction difference between this material and the air around. So if you probe the optical mode, for example here on transmission, and you look as a function of energy, and here this is the position, so this is the size of the micropillar laterally, you find that there are discrete modes because light is confined in all dimensions. The lowest energy mode has an antinode at the center, and so we call it S mode because it looks like an S orbital. And then the mode that is just above has two lobes which are actually out of phase with each other, and it looks like a p orbital, so we call it a p mode. So then you can couple two of this elementary building block. So this is a diatomic molecule, the way we call it. And you see that the S mode now has split into two orbitals which are delocalized over the entire structure. This is the bonding and anti-bonding mode. And you have the same for the p orbitals, actually. You see bonding and anti-bonding mode of the p modes. And then we can continue like this. And this is a 1D lattice where you see we have you have a band, so the modes in real space are delocalized over the entire structure. Then there is a gap. Then you have other bands related to the p bands and so on. And what is beautiful is that you can look also at the Fourier space. So look at the band structure directly optically. Again, this is a raw data image. And you see the S band, which has a cosine shape. So this is really textbook. It's nice if you study quantum condensed matter physics or even quantum, the tight bending approach to use these kind of images. So then how do we describe the system? So you recognize the Gross-Pitayevsky equation. So it looks like the Gross-Pitayevsky equation. So here psi n is the amplitude of the mode on the site number n. You have some coupling between site n and m. You have the nonlinear term, the Kerr nonlinearity that you saw also in the Gross-Pitayevsky equation. This is the energy. And then you see that there are different terms that were not there, which are actually imaginary terms. So this term describes the loss. So there is the loss rate gamma n from photon from site n. And so here we will consider that the loss is the same everywhere. But you could play with non-hermeticity, changing the loss in a controlled way. And then to compensate for the loss, or not actually, but there is a gain, so another term, which is the coherent drive of site n with a frequency, which is omega n, actually I forgot the n, and a phase phi n. Okay, so we are going to look at steady state, for example, because we're not going to be interested in dynamics in this talk, of this discretized driven dissipative Gross-Pitayevsky equation, which is also nonlinear, or driven dissipative nonlinear Schrödinger equation, and it could be called also Landau-Ginzburg equation. This is the same. Okay? Voilà. So, topological photonics with cavity polaritons. So I put this horrible slide. You don't have to look at everything. This is just to say that we are not the only one to work on that this topic has already some history. And so you see some work, for example, in planar cavity. So this is a beautiful work where the Berry curvature and actually all the quantum geometric tensor could be measured, as well as an anomalous velocity. So the idea that you impose a force, but because you have a Berry curvature, you will acquire a transverse motion, and this was measured experimentally. So this is from the group of Lecce from Daniele Sanvito. Then in 1D, this is a paper coming from our group where we had actually demonstrated a topological laser in 1D. This is the work on gap soliton that I'm going to describe in more detail today. And then concerning 2D lattices, so for the moment, only linear physics has been implemented, and there is a report for a topological insulator, but it's not fully convincing, so it needs to be further explored, and this is one of our holy grail for the future. Okay, so we are going to start with a 1D chain, which is a bit like a toy model for topology. So it's called SSH, so this is from the scientists Sue Schrieffer-Heger, who actually introduced for the first time this model, and they were actually interested in the physics of polyacetylene molecules, where you have the alternance between double and single bonding. So you can actually model the system by a chain where you have a staggering of the coupling constants. So you have T and T prime, and you can define a unit cell which repeats along the chain. So you can write the Bloch Hamiltonian of this system, and you can write it like this. So it's a 2 by 2 matrix corresponding to sublattice A and sublattice B, and you have T prime, which is so T is the coupling inside the unit cell that you have chosen, and T prime is the coupling between adjacent neighbor unit cells. So you can calculate the eigenstate of this Hamiltonian, and as soon as T is different from T prime, you open a gap. And then you can also compute the eigenstates, and actually the eigenstates are, so they are all equally distributed on both sublattices, so the modulus of the coefficient for the A and the B lattices, they are the same. So this is the system is completely chiral. This is some chiral symmetry. And then, so the only quantum number that defines a given eigenstate is the phase difference between A and B sublattice. This is phi of k. And so actually you can show that this is what is called the Zach phase. And actually if you integrate this phase over the entire Brillouin zone, you find actually an integer. You can define a winding, and this winding is going to be 0 if the coupling between unit cell is smaller than the intra-unit cell coupling, and is 1 if this is the opposite. So if you are in a bulk, the choice of unit cell is arbitrary. You can choose it like this, or you can choose it like this. So this winding doesn't change the properties of the system, and there is not really a topological property or topological invariant for the bulk. But if you consider a finite chain, then you break the translation invariance, and you don't have the choice anymore. You have to choose the unit cell considering the first dimer that you have when you start the chain. And then what the bulk edge correspondence tells you is that if you start with a weak bound, so if you start with a unit cell with the weak bonding inside, then you will have an edge state if you have a 0 winding in the medium that is there. Okay? So this is a very simple illustration of an edge state which existence comes from topological arguments. If you don't want to play with the edge, because, for example, in our systems we have some strain, we may have some problem when we make an interface with the vacuum, it can be interesting to induce a defect, actually, in the staggering inside the chain. And so this is what is done here. You make a defect in the staggering. You have here a link which is different than the one it should be. So, for example, on this side it should be weak, and on this side it should be strong, so there is something going wrong. So you see that if you have that, you have a boundary between a chain which starts with a weak link and a chain which starts with a strong link, and so you expect to have an edge state appearing at the middle. So now coming to experiments. So we have implemented a 1D chain where we have modulated the coupling. So how do we proceed? So you see that all the pillars, they have the same radius, but the distance between them is modulated. You see that here, these two, they are almost tangent, and here, these two, they really intersect each other. So the coupling between the blue ones here, these two, is stronger than the coupling between these two. Okay? So we see that, so here we have the bands, which are the two bands of the SSH with the gap. And actually, if we look in this region, we see an edge state. And if we look where the light comes from when we monitor the emission at this energy, we see that it comes actually for this green pillar, which is actually a defect. You see that here we have weak link, strong link, weak link, weak link, strong link, weak link. So we have a defect in the staggering. And this is why there is actually an edge state, which is located here. Okay? A property which is interesting, so it's this, as I told you, there is a chiral symmetry, so the eigenstates, they are equally located on one and the other sublattice. And actually, we can define a pseudospin, which is the relative amplitude of a given state between the A and the B sublattice. Okay, so we take a state and we look at this difference. So you see that if it's only on the A sublattice, it's going to be 1. If it's only on the B, it's going to be 2. And actually, the states that are the property of the edge state, topological edge state, is that they are only located on one of the two sublattices. And you see that here. You have here, this is the defect, but then you see that there are exponential tail on both sides, and there is actually only one out of the two sublattices which is bright. And this is the properties of these states which are in the middle of the gap. Okay. So now I want to address the effect of nonlinearity. I take this 1D chain, which, and I'm going to be not at an edge or close to a defect. I'm going to be in the middle of the bulk. Okay? So there is no particular winding. It doesn't mean anything because the choice of unit cell is whatever is the one you want. There is no privileged unit cell. And so what I'm going to do is to drive the system. So you have to understand that when we control the drive, we control the energy of the drive, and at the same time, we control where we want to excite the system. What we are going to do is to drive the system at the middle of the gap of this SSH model. So this is the S band and the bonding band, anti-bonding band. We are going to sit here, and we are going to excite one dimer with the strong coupling. Okay, you imagine that we have dimer with the strong coupling. We excite just one, and we excite it close to the at the middle in the gap. So if there was no line width and there was no nonlinearity, it would be a gap. So I excite, the light will go through, and that's it. But there is some line width. So even if we are in the gap, we are going to excite a bit the tail of the lower energy band. And because if we pump sufficiently hard, this term, so I did not say, but we have repulsive interaction. So this creates a blue shift. So if I pump sufficiently hard, it's going to be blue shifted, the state, and then it will enter more because the absorption will become stronger. And so at the end, I will have a nonlinear effect, which is going to put the states that I'm going to drive resonant to my pump. And then I will form what we call a gap soliton, which is a nonlinear steady state, which is driven by my pump. Okay? So let's say it's a bit better. I'm going to drive a dimer. Because of the dimer, I'm going to blue shift the dimer I'm pumping, and I will create a gap soliton over these two pillars, the central dimer. So this is actually what I'm describing is exactly optical bistability, which is very well known in nonlinear systems. So experimentally, what do we see? We pump the dimer, we look at the transmitted signal. At the beginning, there is nothing, and then there is a jump, and we form a nonlinear steady state. And then there is even a second jump. What happens then is that I start to blue shift also the neighbor pillar. So I will form first a soliton on 1 dimer, and then a soliton on 3 dimer, and so on. So I'm going just to look at the soliton here on 2 dimer. This is the image of the transmitted laser. You see that we have a high intensity here, and then exponential tail. And actually, the soliton that we have has a 0 pseudospin here, because it's both on A and B sublattice. And then it's on 1 sublattice on one side, and on the other sublattice on the other side, so that overall the pseudospin is 0. And this is actually a soliton that was also described previously for what we call a closed system. These are coupled waveguides. So you excite the system and then you let it go. So during the propagation, you don't drive it, you don't lose photons, you can consider that you have a closed system. Here we have really an open system and we drive it constantly. So we were happy to see these solitons. This soliton had already been described, but not in a driven dissipative context. But then, since we are in a driven dissipative context, we can play with the drives. And one thing that we can do is actually, again, pump a dimer, but pump each side of the dimer with a different phase. Here we pump it with 0 difference, with the same phase. So what happens if I pump with a phase difference of pi? Then there is a problem, because the mode that wants to blue shift because of interaction is the bonding mode of the dimer, and I force the system to oscillate out of phase. So what is going to happen is that the system, to reach a nonlinear steady state, will undergo a breaking of spatial symmetry. Okay? It will choose to form a gap soliton either on the left or on the right side of my dimer. So this is what is described here. You can form a bright soliton either on the left or the bright dimer. So we actually managed to form this kind of soliton. This is close to pi. And you see that the soliton, this is the profile of the soliton. You see that it's located essentially on 1 pillar, the violet one. It has actually a chiral tail, so there is an intensity in 1/2 pillar, and there is no signal on the other side. So this soliton has a finite non-zero pseudospin. So this is a steady state that you cannot get if you don't force the system to stay there. It's unstable otherwise. And if you think about who is blue shifted and who is not blue shifted, you see that since the soliton is located on one side, if you look at the states, what happened in the chain, actually, you have blue shifted one side and the other one is not blue shifted. So schematically, you can say that we have cut optically the chain. There is then a winding, a chain here which finishes with a strong bound, and here a weak bound, and so you should see an edge state occurring somewhere. So where does the edge state occur? It occurs in the excitation spectrum that you have on top of this nonlinear steady state. So it's in the Bogoliubov spectrum that you expect to see an edge state. So we are on the way of measuring the Bogoliubov spectrum, but in the paper, we did not have the setup. So what we did is actually calculate the Bogoliubov spectrum. So what do? We have we say that the wave function now is the nonlinear steady states that we have formed plus a variation of the wave function. And then we do the usual Bogoliubov transform. So we calculate a normal and a Gauss branch, and we compute that for the whole structure. So you see the bands, which are not modified because we only pump the dimer. You see that the dimer, the site of the dimer is blue shifted. It's here, actually. It's completely going out. So you see that the bands are cut here. We have cut really the chain. And we see an edge state in the Bogoliubov spectrum. So this was the first hint that actually pumping the system, driving the system, we can induce topological properties here in the excitation spectrum. Okay? So we were super happy with that. We are working to see that. And then we were thinking, brainstorming with Sylvain. And we thought that maybe it could be nice to actually pump the whole chain, not only one dimer, and see what we could do. So this is theory. This is not experiment. That's why there is going to be proposal on top so that you know that it's not experiment. So we take a chain. So here it's not SSH. It's just a regular chain, just identical sites and identical coupling. So with a very simple band. And we pump the system. So here we are not going to play with the phase. We are just going to play with intensity. So we pump all the sites, but we induce a periodicity in the drive. So for example, here I'm going to take 5 different sites, so a unit cell of 5 sites, and I'm going to reproduce it periodically over the entire chain. Okay, there is F1, F2, F3, F4, F5. And we are going to consider, so here, so there is a periodicity. So you see here, N is going to give you the spatial periodicity. And there is a phi, which is for the moment equal to 0, but that we will vary later on. You see where I go. I want to make a tau-less pump. Okay? So that's what we do. So we consider a number alpha, which is P over Q, and we are going to take only integer. So let's start with P equal 1 and Q equal 5. So if we pump the system, we pump it in the middle of the gap again, and we increase the power, and we can reach a steady state, okay? So where we have put some states in resonance with the pump, and others which are not pumped enough, they will stay in a linear regime. And so we get a fluid, a nonlinear steady state, which is modulated in space. Okay, this is the number of unit cells, so it is something which is periodic. Now, if we look at the Bogoliubov spectrum, alors this is terrible, huh? Don't look, you don't see anything, that's normal. Just what we do is we consider again the steady state plus some modulation, and now we have actually 5 sites to consider. And for 5 sites, we have then a ghost and a normal branch. So we have a 10 by 10 matrix. This is this, you can count if you want. It's 10 by 10. Okay, U1, U2, U3, U4, these are the normal, the distribution of the normal branch on the 5 sides of the unit cell, and then you have the same for the ghost branch. So what is convenient is actually to see that we have 2 blocks, 2 main blocks, which are 5 by 5, and then there is some coupling between U and V sector. And this coupling can be neglected in many situations. So I'm going to consider situations where we can forget about the other term and just look at one of these blocks. For example, the U sector, the normal branch. What do we see? We see actually the Hamiltonian, the regular Hamiltonian from which we started, plus on the diagonal, some Kerr term. So this means that because of repulsive interaction, these sites, they are modulated. They have a periodicity of 5, and they are modulated according to the amplitude of the nonlinear state on this site. Okay? So when you have an Hamiltonian like this, and you diagonalize it, so we can remove the imaginary term because it's always the same, so it's going to be imaginary term times identity. We don't care. And then we have a real Hamiltonian that we can diagonalize, and we get 5 bands, 5 normal bands and 5 ghost bands. On-site energy modified by the Kerr energies. So that's it. That's the 5 ghost branch and the 5 normal branch. So then this is for phi equals 0, and then the idea is that we are going to change 5. We are going to modulate the pattern of excitation power that we have. So that's one possibility. So we are going to modulate it according to this So it's modulus of cosine. And you see here the evolution of the pumps as a function of phi. So the nonlinear state, what is going to happen to it is going to move the nonlinear state because we move the pattern of excitation. So that's it. That's one example. We take alpha equal 1 over 5, and we see that as we modify phi, we see a variation of the pattern. Okay? So then what does it mean? It means that the on-site energy of my 5 by 5 Hamiltonian are going to change in time according to the Chaire interaction on each side. And so what is going to happen is that you are going to modify your bands according to phi. Okay? We form now 2D bands. So we have a 1 plus 1D system. One direction is the regular K. The other one is a parametric dimension which corresponds to phi. Okay? And then we can actually show, and it has been shown, that this kind of Hamiltonian, which is parameterized by phi, by a phazon, which is a parameter, which is modulated adiabatically and slowly and periodically, you can actually show, so make a Fourier transform actually of the dependence of phi. Because it's periodic, it's going to be a discrete Fourier transform. And so then you can actually show that the Hamiltonian is equivalent to a 2D Hamiltonian, so with the regular spatial dimension plus a parametric one, and the modulation in time introducing a complex coupling constant in the parametric dimension. And this is actually exactly the Hofstadter model. And so you expect to have, depending on alpha, Chaire numbers for your 1 plus 1D bands. So that's what we can do. So we worked with Nathan Goldman. He knows by heart all the Chaire numbers of the Hofstadter model. And so for alpha equal 1/5, you know, everybody knows, according to Nathan Goldman, we did not, but now we know, that you get finite Chaire numbers. So for these bands, you have 1, 1, minus 4, 1, 1. There is a rule, the total Chaire number should be 0. If you sum everything, you should recover 0. Well, that's super cool, but then how do we show that we have a tau-less pump? Because we are modulating a system on 1D, and we know that if we take a particle, it should move, actually, depending on which band you put the particle, after one cycle, it should move by exactly the Chaire number of the band times the unit cell. So where can we find something which is localized? Actually, what is localized in this kind of system are the Wannier states. The Wannier states, they are states which can sit in one band and are the maximally localized state that you can form. And so we computed the Wannier state of each band along the protocol. And what we could show is that indeed, for example, in these bands, which have a Chaire number of 1, you see that the Wannier states move by 1 unit cell, whereas in band 4, it moves by 4 unit cells in the opposite direction. So we are super happy. Okay, so we have a protocol which implements a tau-less pump. What is also very interesting is that actually here we have considered that the system is harmonic, that we have only one harmonics in the protocol, which is the one that we impose with our pumps. Actually, the Chaire nonlinearity, so we see that the modulation is J psi square, and this is actually not harmonic. If you increase the power, you start to have non-harmonicity in the protocol. And actually, so we could show in this 1/5 that if we look at, so here we are going to look at the function of the power, and you look first at this curve, the blue one. We look at the gap between the third and the fourth band, the 2D bands. And what we saw is that actually the gap closes and then reopen. And when we look at the band structure here, actually we have a band inversion. We compute that the Chaire numbers are inversed. You see that here we had 1, 4, minus 4. Here we have minus 4, 1. And we see that indeed the Vanier states, they have changed their motion because we have made a topological transition. And this is the non-harmonicity that creates that. So then we were a bit embarrassed because if you look at the power at which it occurs, so this is actually a threshold for really a different nonlinear steady states to occur, and we washes out completely the topology. We come back to the beginning. And you see that the topological transition occurs at 0.99. And so it's so close, so that's why we chose this kind of scale. And it's so close to 1 that experimentally is going to be very tricky to see this transition. So actually the idea we had is, okay, now that we have understood that non-harmonicity can create topological transition, why not introduce it directly in the pump? So that's what we did here. We put a bit of non-harmonicity in the drive, and because of that, we see the transition before, and this should be observed experimentally. Okay, so we did that also for other values of alpha. This is what alpha equal 1/3. This is alpha equal 1/4. 1/4 is nice because you have a gap actually in the band, Dirac cone, which open, and you see the opening of a gap when you start to have this nonlinearity. So this is a nice proposal, and this was a proposal, and the experiments are underway. So where am I? I have 3 minutes? More than? Okay, I go quickly because this is more easy, I think. This is so coming to 2D, 2 dimension. So this is just an example, a honeycomb lattice. So it emulates the physics of graphene. You know the band structure of graphene. It looks like this. We can measure it. So here we have Kx and Ky, so 2 angles, but we can really make a tomography of the band and so see directly. So this is a measurement of the band structure of a lattice like this. We can really completely see the band structure. So now I want to come to Bloch modes. And so this is a work that was developed really by Sylvain. And so to demonstrate the method that we want to show, we took a system which is gapped, because when the system is gapped, you can define a Berry curvature, and it's a nice way to show that. So we took the analogous of HBN. HBN, it's again a honeycomb lattice, but now we have 2 different on-site energy on A and B sublattice. So the way we do that, if you look carefully at this honeycomb lattice, we have smaller and bigger pillars. And the smaller pillars, the light is more confined, and because of that, the mode is at higher energy. Okay, so this is A and B sublattice, and they don't have the same energy. And because of that, if you make, so here it's a cut of the band structure, you see that there is a gap. Okay, so this is a gapped honeycomb structure. So now if we look at the eigenstates, so the Hamiltonian is this one, it's very well known, the Hamiltonian of graphene. And so you can compute the band structure, and you can write the eigenstates. So differently from the graphene or for the SSH model, here you see that there is not only a phase difference between A and B sublattice to characterize the eigenstate, but there is also a difference in amplitude. So we can actually mark an eigenstate by 2 angles. So we can plot the eigenstate on the Bloch sphere, and so each eigenstate will be characterized by theta and phi. And so, for example, if theta is equal to 0, then you see that we are located only on 1 sublattice. So the north pole is full localization of on A sublattice, and the south pole is B sublattice. And if you are equally distributed, you lie in the equator. Okay? And so the band, so these are the eigenstates. So if you compute theta and phi, this is theta, so the relative amplitude between the 2 sublattices in the Brillouin zone. And so what you see is that there is a very strong localization on one sublattice, so when theta equals 0, actually the sublattice, so here you are located only on one sublattice at the in the Dirac valley, at the K prime point, and you are more located on both sublattices, equally located when you are at the center of the Brillouin zone. You see that if theta is equal to pi over 2, then you get cosine pi over 4, sine pi over 4. You have the same amplitude on the two. Okay? What is very well known is this winding of the phase phi, the difference of the phase between the two sublattices. So there is a singularity at the K and K prime point, and this is possible because you are located only on one sublattice or on the other. So phi is not well defined exactly at the singularity. There is a singularity, and you have a winding in one direction or in the other. And because of this singularity, you can compute the Berry curvature. So we come back to this expression that we saw in the almost the first slide, which is, so this Berry curvature is given by the derivative of this Bloch state in K space. And you find that the Berry curvature is almost vanishing everywhere except at the K and K prime point, and it has opposite values at K and K prime, so that if you integrate, you get a zero-charm number. Okay, so the idea we had was, can we measure that? Can we measure the Bloch state so that we can compute the Berry curvature and potentially non-zero Chaire number if there are non-zero Chaire number? So you see that we have to make an experiment which is resolved in sublattice to be able to measure the relative intensity and the relative phase. We have two angles to measure, okay? And to measure two angles, we need 4 measurements. So then comes a bright idea, which is to use an SLM, a spatial light modulator. So what do? We have our sample, our honeycomb lattice. We collect the light, and then we project the light, the pattern, onto the pixel of a spatial light modulator. So you have to imagine that we have a spatial light modulator with very, very small pixel, and we project this emission, which is the emission of the S-band of the system. And you have to understand that the pixels are much smaller than these bright spots. So we have several pixels per site, and we can control the phase of the reflected light using the spatial light modulator. And then what do? We project the Fourier space of the corresponding emission. So if we don't do anything, we don't imprint anything on the A or the B sublattice, so we get the image that we call A plus B. Then, because we have a polarizer, we can actually also cut the light, so we are able to image the dispersion when we have only illuminated the emission from the A sublattice, when we have only the illumination from the B sublattice. So these are 3 measurements. We are missing one. The other one is going to be A plus IB. We impose a pi over 2 phase difference between A and B sublattice. And we measure the dispersion. These are the 4 measurements. So you see things already. You can already understand some things. So for example, if you look at this image, this is the one that we usually look, going to the gamma point, through the gamma point. You see that this band is very bright here, and this one is almost vanishing. Why is it? It's because this band, this is A plus B, and this one is A minus B. And A minus B means that you have a destructive interference between the two bands. And this you see directly. Actually, if you look at ARPES measurement on real graphene, you will see that too. It's also very faint, the upper band. Now what you see is that if you take A plus IB, you destroy these destructive interferences and you recover a nice anti-bonding band. Okay? What you can also see is that if we look close, so here this is A only, and you see that the lower band, and especially close to the K point, is very, very faint. And it's the opposite if you go to the B site. And this shows you some information about the localization on one or the other sublattice when you are close to the Dirac point, the Dirac valley. Okay, so this was just hand waving, but then computing this image, we can actually recover theta and phi. And this is what we do here. This is for the lower band, theta and phi, and it looks quite nice compared to the theory. Okay, we did the same for the upper. And then what is nice is that we can compute the Berry curvature starting from our measurement, so the measurement of the Bloch state. This is what we get for the lower band. This is what we get for the upper band. And we see clearly the Berry curvature with opposite sign. Okay? So we are writing the paper. Meanwhile, we did also other experiments. So this kind of experiment have been done already, in particular with cold atoms. But so far, the only techniques that were implemented were for two-band model. Actually, we can work with this technique with more than two bands. So for example, we can include the polarization, then we get a four-band model. This is where we can get a real topological insulator, and there is no reason why we could not measure both the sublattice degree of freedom and the polarization degree of freedom. So this is something that we have already implemented. We can also work with the p-bands. So then we have actually 6 bands. If you do that, you have the 2 S-bands plus the 4 p-bands. So there are p-bands in the graphene, which we have actually studied already. So here, these are the band structure that you expect when you take px and py on each side of a honeycomb lattice. You expect to have 4 bands, and there are very interesting things going on. You have actually Dirac cones here with windings, which are of plus or minus 1 times 2 pi, as in the Dirac cones of the S-band. And you have also a winding of 2, actually, at the touching point between this parabolic band and the flat band. And we have also studied what happened to this band structure when we apply strain. I don't want to go into the detail, but this, for example, this touching point splits actually into 2 Dirac points, and these 2, they have the same winding, contrary to the other one which are there. So we are actually implementing this tomography technique to take into account both S and P mode, and we recover, actually, we can measure directly these windings and go to also very interesting multi-band topology that I don't have time to discuss. So it's just to show you that we have actually, playing with the fact that we can measure the phase, we have a great tool to go into deep into the topological, the linear physics, and then nothing prevents us to join the two, look at Bogolyubov, try to see also the phase of the Bogolyubov mode, but this is for next Séminaire at Collège de France. Okay, so I'm going to finish now. I told you that nonlinearity can actually change the topology of the Bogolyubov spectrum, so it's really a novel playground to play with the topology. There is also a very nice proposal in 2D where you can see the emergence of edge states because of the drive. And then this tomography technique, which is extremely promising. And with this, I thank you very much and apologize for not being so strict with the time as Jean is always.